Amazing. Hello, everyone, and welcome to another exciting Center for Education and Neuroscience seminar. My name is Yasin Arslan, and I'm a PhD candidate at UCL Institute of Education. Today, it's my great pleasure to introduce Professor Torkel Klingberg from the Karolinska Institute in Sweden. Torkel Klingberg is a professor in cognitive neuroscience, and his research focuses on child development and the training of cognitive functions during childhood. He published the original articles showing that working memory can be improved through training, which in turn reduces inattentive symptoms in ADHD. Recently, his research has expanded to explore the environmental and genetic influences on cognitive development, including the impacts of socioeconomic studies on cognition, the effects of screen time on intelligence, and the interplay between genetics, cognitive training, and mathematical models. One notable study involving 17,000 children demonstrated far transfer effects from cognitive training to mathematical learning. The work has been published in journals including Science, Nature Neuroscience, and PNAS. Torkel has received numerous scientific prizes and is a member of the Nobel Assembly. He is also the author of popular science books like The Overflowing Brain and The Learning Brain, which I'm reading with interest. In today's session, Torkel will give us a talk on the effects of working memory on math development. If you have any questions, please put them in the chat and we will address them after the talk. Now, over to you, Torkel.
Thank you very much. It is a pleasure to be speaking here since education is very close to my heart and education and neuroscience is such an exciting combination. So my field is working memory, and let's see if I can advance the slides. Here we go. This is an example of a working memory task. Here, you should remember where the person points so that you can point at the same boxes in the same order. So here you see the finger. And now you are keeping 4 items in working memory capacity, 4 positions in working memory capacity. So you can point at the same positions in the same order. And this is visual information and it's spatial information. So we call it visuospatial working memory. And this is a very simple task, of course, and this is not what we do. We use our working memory for every day, but it's also used, for example, for remembering plans of what to do next. If you have the plan to go into the next room and pick up a specific book, it's a plan you keep in working memory until you've completed it. Or if I ask you to do a mental task, such as multiplying 7 times 14. Now, take 2 seconds to do that. And if you notice what you do, if you do as most people, you probably first take 7 times 10, and then you remember 70. And then you remember that the question so that you know that you also need to do 7 times 4 and 28. And now you add 28 to the 70 that you keep in working memory. So cognitive tasks like this often require several steps and that you keep the information from each step in memory. So we use this memory as a kind of a workbench for mental tasks, hence this term working memory. And similarly, if you read a long and complicated sentence, you need to remember the beginning of the sentence when you reach the end. And you use your working memory for that. So it turns out that even simple tasks, such as this one, the visuospatial working memory task that I just demonstrated, if you measure the capacity here, which means that how many boxes, how many positions can you maximally retain? It's a pretty good measure that correlates with a lot of stuff. For example, it correlates surprisingly high with fluid intelligence. It predicts school performance, not only how you perform or how the kids perform at the same time, but also how their school performance will develop over several years. And this is important work that has been done by Susan Gathercole, among others. And if you measure working memory capacity in a group with kids with ADHD diagnosis, you will see that they have lower working memory capacity than children without ADHD. And it's specifically the inattentive symptoms that are linked to working memory deficits. And this makes sense from a neuroscientific point, because we know that the networks for attention, for controlled attention that is, and for working memory are largely overlapping. If we go and look at the brain areas involved in working memory, they have been mapped in both animals and humans with various techniques. And if we keep to visuospatial working memory, the green regions here, can you see my pointer?
Yes.
Yeah, the green regions here are key regions for visuospatial working memory. And it's actually so informative that we can do brain scanning of these regions and get a rough idea what kind of information a person is keeping in his or her working memory. This is visuospatial working memory. There are other types of working memory. For example, if I give you a series of numbers, 1, 3, 6, 8, and ask you to repeat them backwards, you will see partly other areas activated in the brain. It's those red areas here connected to the language networks. But there are also overlaps, some areas that are similar for both visuospatial working memory and verbal working memory. And this fact was a key observation for getting us started in trying out working memory training. So let's say that you could train the areas involved in one type of working memory. If the areas are partly the same for other types of working memory, you would expect to see a transfer from one type of training to other non-trained tasks. So we started to try to train working memory. This is now more than 20 years ago. And the primary objective was to try to improve working memory. And we expected that since it's linked to inattentive difficulties, we would expect to see less inattentive symptoms in children with ADHD. And this became later known as the Cogmed working memory training, connected to a company which I still have a connection to. And this is some data from one of the original studies showing working memory capacity in a comparison group in white and a treatment group in green. So the treatment group did working memory training with adaptive tasks close to the capacity limit. That's where we expected to have the training effect. And the comparison group used a similar data program, computer program, but with low working memory loads. And then they were measured before training, after training, and at a 3-month follow-up. So we could see that they improved on the trained tasks, but it also transferred to non-trained tasks. And we could also see that it decreased the inattentive symptoms in children with ADHD. Since then, there has been a lot of standards, hundreds of studies on working memory training. using not only this Cogmed method, but other types of working memory tasks that have been used for training. Here are 6 meta-analyses looking at the transfer from trained to non-trained tasks of working memory, showing the effect as effect sizes, and that means how much do the training group improve compared to the control group, and expressing that in terms of standard deviations. When it comes to inattention, there's also been many studies. In this case, this is a summary of Cogmed training studies, mostly in ADHD, but also in other groups, such as children born early, or older subjects who also have working memory deficits. And on average, we see a significant improvement in inattentive symptoms in everyday life. This has also been confirmed most recently in this study by Westwood, where they looked in a meta-analysis of computerized cognitive training, specifically in attention deficit, hyperactivity disorder, and found a significant improvement in inattentive symptoms. The neuroscience has also been progressing, and it's been studies done with humans with various techniques, so different methods for measuring changes, measuring brain activity during task performance or during rest. And what they show are many different things, of course, but a common theme is that we can see a strengthening of connectivity between these key networks in this working memory network. What has been unclear for a long time is the transfer to specific academic performance. And this is a overview of studies using the Cogmed method and some kind of math outcome measure. So in green are those showing effect sizes larger than 0.25, in red less than 0.25, and stars for the significant effects. So we can see that although it's a majority of studies finding an effect, there is also a lot of differences between studies. And this can have many reasons. Firstly, it is to be expected that there are large differences between studies just because of small study groups and some noise. They are also using different outcome measures. So we would not, for example, expect that children acquire novel mathematical concepts just by improving their working memory capacity. But it would be somewhat mathematical tasks that could be affected more than others. The 2 largest studies are the one by Roberts et al., and they had children with low working memory. So they had problems in many different areas, and they had 450 subjects and did not find an effect for mathematics. On the other hand, there is a more recent study by Eva Berger and Ernst Fehr, looking at almost 600 children from the typically developing population. And what they did was also looking at follow-ups 6 months after training and 13 months after training. And what they found was immediately a small effect here for geometry around 0.2 that was not even significant, although they had almost 600 children. 6 months later, it had increased to roughly 0.25 here. And after 1 year after training, it was 0.4. So it gradually improved. And the control group in this case did ordinary classes, mostly mathematics. So a few hours of training was better than doing mathematics, not for learning arithmetic facts, but for more cognitively demanding aspects. They also saw a gradual increase in reading abilities and even in performance on the Ravens IQ test. When they followed up the kids 3 years later, they saw that the children who had participated in the training had 44% chance of entering the academic track compared to roughly 28% in the control group. So that was 3 years after training. So this is a puzzling effect. And we wanted to further dig into this question in a large study where we combined different types of cognitive training with mathematical training. So we developed an app, did research on it, found an effect, and later put it out freely on App Store, and it was used by schools. So it was used, or we analyzed in this case, data from 6 to 8-year-old children, and more than 17,000 of them who did 7 weeks of training. And except for the mathematical training, which was the same for all participants, some of them did more of visuospatial working memory, some did more of nonverbal reasoning training, and some did more of rotation training. So both nonverbal reasoning and rotation are expected to give to be having a positive effect, to be related to mathematical performance. Children were then randomized into different training groups with different amounts of either working memory, nonverbal reasoning, or rotation training. And then we had built-in math tests during the first week, 5th week, and 7th week. And this was tests of addition, subtraction, and number comparison. And they were different from the tasks used in the training. So for each kid, we can get 3 performance measures like this from the first week, from the 5th week, and from the 7th week. And then we can draw a line between these points to get an estimate of how much they improved. So the slope of this line is what we're interested in measuring. So to the results. When we compared training plans, we found that it matters what kind of cognitive training they used. So if cognitive training was totally meaningless, all kids would improve equally much. It would not matter if they had working memory or rotation training, but we could show that it matters, and this with a very high statistical significance. And both NVR and working memory training was better than using rotation training, which in itself is probably not a meaningless activity, but nevertheless, we saw that these activities promoted mathematical learning. We could also see another interesting thing. Here we look at the impact of working memory training on math learning. And each group of bars here is kids with different baseline performance in working memory. So here is the effect on the average kids, and we compare children having 4 minutes of training, work memory training per day, with maximum of 16 minutes work memory training per day. So what you can see here is the difference is roughly 0.2, which is the same as in the study by Berger and Fear. When we look at children who had relatively higher work memory at baseline, the effect was larger. And when we look at children who had impaired working memory from the start, the effect was smaller. So this is an example of a rich get richer effect, meaning that those children with difficulties, initial difficulties, they are also slower learners. So to really see mathematical improvement in this group, they would need 2 or even 3 times as much training as kids in the other groups. So this was interesting also because it explained the differences between the Roberts study and the Berger and Fear study. The Roberts study probably testing kids in this group while the Berger and Fear trained kids mostly in this average group. But again, we should not think that this is a indication that you shouldn't do work memory training if you have work memory deficits. It's just that it is large differences between individuals, which we wanted to further understand. So this is what we did in the next study. So here we compared improvements from work memory training with improvements just as a result of aging. So as children get older, they get better and better work memory capacity. This is illustrated by this blue line here. The red line here shows that children, when they do work memory training, they improve over training days here. But the interesting part here is the bottom graphs. So this shows the difference between individuals. So there are large differences among children in how much they improve with age, as well as how much they improve with training. So even keeping to the normal range here, we see a roughly 3-fold difference in how much they improve. So what we wanted to know was, is there any similarities in the reasons for these differences? More specifically, our hypothesis was that there will be genetical differences that could explain this variability. So we used what's called a polygenic score for cognitive performance, which is very similar also to the polygenic score for educational attainment, and related the changes in working memory in both groups to the genetic score. And then we could show that this score significantly correlates with the improvement in both groups, and that there was no interaction between the groups. So this points to a genetic difference between individuals, explaining part of this variability. So a kid has low working memory, partly because of genetic differences. And the same differences can also then partly explain why it takes more time for some children to improve. We are also interested in the different aspects of what is happening, actually, the mechanisms during training. So to address this, we looked at data from 1,300 children, aged 9 to 11, and they did 8 weeks of Cogmed work memory training. So this is one example here in A of one of the trained tasks. Then at 5 different time points during these 8 weeks, they were tested on these 3 tasks. An odd one out task, which is a visual-spatial working memory task, but it's not trained. A following instructions task, where the children hear a verbally spoken instruction. For example, take the red crayon and put it in the gray or in the green box, and then touch the blue bottle. And then the instructions get longer and longer. And then we have a math task with addition and subtraction tasks that get gradually more and more difficult. So what we see here, we can look at to the right first. Here is improvement on the train task, the grid task with the robot that I showed. And here's the gradual improvement on the transfer tasks over these almost 40 days of training. What we wanted to know was, is there two different processes happening at the same time? So we tested this in a factor analysis model where we have one factor representing improvements that are specific for the trained task. So it's a task-specific improvement. And another factor that would be common for all tasks, which would represent a capacity factor, a more general working memory capacity. And this model proved to be a pretty good explanation for what's happening here. So in red here is the total improvement that you can see during training. And then the yellow one shows how they improve on the specifically trained task. So that is task-specific strategy, so to say. And in the green is a capacity factor, which then is increasing gradually over these 5 weeks. So that this is an explanation for what's happening during work memory training. First, you see a quick improvement because you get to learn to perform this specific task. But on top of that, there is a slow and gradual increase in capacity that generalizes also to non-trained verbal tasks and to mathematics. So the conclusions for this, what we think is, we see so far is that working memory can be improved by training. And we see effect sizes of around 0.6 for this improvement. The neuroscience suggests that training enhances the connectivity between key brain regions, in particular frontal and parietal regions. And improving working memory decreases inattentive symptoms in ADHD with an effect size of around 0.2 to 0.5. And improving working memory also improves mathematical learning, but there is a larger variability between individuals in this. So I think that this is a field that is still developing. We need large trials, homogeneous trials with many participants and using good outcome measures and long-term follow-up. And we also need to take inter-individual differences into account. Thank you. And I look forward to listening to your questions.
Amazing. Thank you very much, Torkel, for this great talk. Now we have some time for questions. Actually, I would like to start with a question of mine, but I saw a question that is more relevant to my question. So I will get Lloyd's question from the chat first. So Lloyd asks, within the studies, the 5 meta-analysis studies focusing on developing working memory, do we know what specific programs they used?
Yeah, that is always documented in these meta-analysis. Yeah.
Okay.
So it was a mixture of different methods. The 6 meta-analysis I showed how training improves non-trained measures of working memory. Yeah.
Okay, I see. Because he wonders whether this can be replicated if the details are given. I think yes. The answer is yes. Okay, over to my question about the meta-analysis. Well, you presented that there are varying degrees of improvement in working memory capacity following these different training, although almost all showing the increase. But what do you believe accounts for the variability in these results? So you talked about some polygenetic scores, but are there any other specifics that you encounter?
No, we know behaviorally that there is a rich get richer effect. So if you have a better performance at baseline, you would gain more, which is unfortunate. and unfair, so to say, but it should be rather an indication, I think, that some kids need more training than others. The explanation is probably both in environment and heritability, as always. It's just that we know now that this specific measure linked to cognitive performance and educational attainment is important. In another study, we have also looked at socioeconomic status and in relation to working memory performance, development of working memory, and brain development. And that is also a factor in this. And we know, of course, that there are many detrimental environmental factors, such as negative long-term stress, which is often associated with low SES, that can affect working memory capacity and training.
Great. And we have a question from a familiar face, Tracy Tokuhama Espinosa. So she wonders, would increased training time further improve inattentive symptoms?
Well, the answer so far is yeah, up to the amounts of training that we have tried so far. So, for example, up to 8 weeks of training and various amounts of minutes per day, it is roughly linear to the amount of training. If you keep the type of training constant, it's roughly linear. But I would assume that, of course, that there is an asymptote. There is also probably an asymptote in how much you would benefit in everyday life. For example, if working memory capacity is the weak link in your everyday performance, there's probably an asymptote that will be reached, but we don't know exactly where.
Thank you, Torkel. And we have a bit more general question about the participants or subjects. So Sandra Elliott wonders, have you looked at subjects with dyscalculia?
No, not specifically. I mean, although it's known, of course, that mathematical ability has a correlation with ADHD, and ADHD has been studied, but not subjects selected specifically because of dyscalculia, as far as I know.
Okay, thank you. And we have another question from Ali Nouri. Thanks for the great presentation. I want to know, how do you see the future for working memory training with advances in AI technology? Do you suggest to design training programs informed by neuroscience using AI tools?
It's an exciting possibility. It's possible. I think that we and others are experimenting a lot with AI right now, and hopefully we could improve the methods further. We have, for example, we are playing around with methods to characterize the cognitive deficits or cognitive profile of our children, and optimizing the training paradigm, so that it would be one possible way to do this.
And I think, as far as I know, the Cogmed training, the working memory training, has also been translated into many, many languages. So I think we'll be able to see results from other contexts too soon. That's what I hope. Is that right?
Yep.
Okay. Okay, let me get another question from the chat. So Esther asks, some of the trainings gets boring after time, particularly for children with ADHD. So it would seem that those children who really need the training may not give it their all after a few sessions. Would that get in the way of results?
I think it's a practical problem of getting children to actually do the training. I mean, It's a problem with all type of training, right? Even going to the gym, that's one of the main problems. It's so boring. So that's why not everyone is doing it, even though we know we should do it. I think it's especially large problem in children with oppositional defiant disorder. That's one of the groups that has had most problem in completing this working memory training. So the really typical user would be more towards the ADD area. So what's previously called ADD, which is the attention deficit hyperactivity disorder, but predominantly inattentive problems.
Thank you, Torkel. We have a bit long message, so I will try to keep it short. So Catherine wonders, I'm wondering if or how working memory is linked to visual attention. She says she's a master's student of education neuroscience, and they've been looking at visual factors behind reading difficulties. Also, her daughter has Erlin syndrome and has done vision therapy exercises, and they saw some improvements.
Yeah, I didn't have time really to go into the details, but as I see it, the work and as many researchers see it, this is not controversial. Visual spatial working memory is partly the same thing as spatially selective attention, controlling your attention. So there are many types of attention. There's the arousal level, which is kind of non-specific activation. Then there is the bottom-up attention, so reacting to novel things in the environment. And then there is the top-down attention or controlled attention. And it's the controlled attention which is overlapping with working memory, and where we see the problems in kids with ADHD, for example. So it's those areas that I pointed to in the beginning of the talk there. They are all involved in top-down attention.
Thank you, Torkel. Let's take another question from Katie Ellen. So, the evidence you have presented shows near transfer and maybe some less near transfer to a specific arithmetic task. Many studies do not show any effect for far transfer to subjects studied in the classroom. For example, a test assessing all aspects of maths. Why do you think this is?
Well, I think that you would expect to see transfer when it's a working memory demanding activity, right? When it demands visual spatial working memory capacity, which and control, top-down control of attention. So for example, long-term memory, it's encoding into long-term memory. It's not necessarily the same aspect. Many aspects of language, for example, are not the same. It's different systems of the brain. If you can see transfer to inattention in ADHD and improvement in mathematical ability and nonverbal reasoning, as we saw in these 600 children, and as we saw in our 1,300 children, it's not everything, no, but it's good enough.
That's promising. And let me ask a very broad question, Torkel. Given the positive outcomes associated with this working memory training in improving math learning, how might these findings be integrated into educational curriculums?
Well, if we see now that 30 days of training, roughly 20 hours of training has effect on the outcome, even not only math tests, but on the outcome and entering of the academic tracks 3 years later, I think it's a pretty cost-effective way of helping children. And one should look at ways to scale it up and find the right way to do that.
Amazing. Okay, Torkel, thank you very much for your time. And I think we have taken all the questions. So one last one from Tracy. What definition of working memory capacity are you using? Time versus processes?
Well, in our case here, it's pretty straightforward. I demonstrated in the beginning there a simple visual spatial working memory task where you can increase the number of positions to keep in working memory. So that is the amount of information that can be kept in working memory. It's not increasing the delay, going to longer and longer delays, but looking at the amount of information.
From a more practical side for education, Esther asks, what is the best assessment tool to get an accurate working memory score for children?
Yeah, it's a tricky one. Susan Gather-Cole and Tracy Alloway developed way back a test set that could be used, that we've been using. Unfortunately, I don't think it's available any longer. I think the task that I showed in the beginning here, which is called the spatial span task or the Corsi block tapping task, it's a pretty straightforward measure of visual spatial working memory. So I've no straightforward, easy answer to give there unless you have access to neuropsychological tests. But there are also many signs in everyday performance indicative of working memory deficits, such as problem following instructions, for example.
Yeah. And I think that can also be one of the recommendations for parents, for instance, because they may not have access to such tools. What do you think can be one of the significant symptoms of working memory difficulties that parents can see or identify? Or like, let's say flagging.
It is parents, they don't always know about the concept of working memory. They would say that the kid has problem paying attention. Yeah, that they are easily distracted. Problems following instructions. Yeah.
Amazing. Torkel, thank you very much for your time. And we had really nice, interesting questions. And I'm so glad we had time to answer all these questions. To all the participants, to all the audience, you can email your further questions either to me or to Torkel's email if you want to know more about the field. That's all for today, and looking forward to our next talk next week. Torkel and all the audiences, thank you very much for your questions and your time.
Thank you very much for your attention.
Let's stop recording.